Hey, welcome viewers. Today I want to do a continuation video on reading circuit diagrams or wiring diagrams and troubleshooting circuits. So this circuit was in my previous video and it was an oven heating element circuit. And we were troubleshooting the problem of why the heating element depicted by this little castle looking circuit component here is a heating element, right? Why the heating element was not heating up. However, the power indicator or the element, the indicator that shows whether the element has power or not to it, was always on, even though the switch here was always off, right? Or no matter what position it was, there was no heating, there was no heat from the element, and the power indicator was always on. So I'd like to just go into a little bit more of a deep dive on how this, this simple circuit works, right? But how we can often miss out on the little details when especially when we're talking about 240 volt circuits. First of all, given this diagram, let's get into why we know that it's 240 volts in the first place. Well, the reason why we know is because we have here depicted here line 1, neutral, and line 2. That is how we know in a wiring diagram that we're dealing with 240 volt circuits here. All right. So let's get into troubleshooting this thing, looking at deep dive on how this particular circuit works. Because once we know how this circuit works, we are probably more able to troubleshoot more complex circuits down the road. So let's get into it. And let me just preface this this video in saying that a lot of us have, training in reading circuits from high school, and mainly we deal with direct current, right? And I have to tell you that when we're dealing with household appliances, most often we're troubleshooting circuits on the outside. Like, we're not looking at the internal microcontroller components, computer controller components. We're looking at simple simple loads here, right? Like heating elements and things. Those things are usually powered by the AC that's coming from your house, right? The AC current. When it gets into the computer side of things, it goes into direct current. And I think, at least where I come from, mostly the education that has been given, at a high school level, we do touch into alternating current and the theory of it. But when it comes to reading circuitry, it's most often taught in terms of direct current. And there is a reason for that, and we'll get into that later, right? So what I have here on this screen is what I call the just the wires that are available that are coming out of your ovens. Your kitchen has an outlet which has 4 prongs on it, right? And the 4 corresponding wires are hot 1, neutral, hot 2, and ground on there. So when we look at this diagram, take a look back at this diagram here in the circuit diagram. This is overlaid. When we look at this one, we notice that line 1, neutral, line 2. I did not draw ground on there because that's another discussion we can have at a later time. Okay, ground and neutral are bonded together in your house, so they are one and the same, but they have a different purpose, and we shouldn't mix that up. But anyways, line 1 is hot 1, neutral is neutral, and line 2 is hot 2. So if we take a look at this one back into our generalization here, that's what we have, right? So let me just write that down in here so that we don't forget. hot 1 is line, we can treat that as line 1, neutral is neutral, hot 2 is line 2. All right. So let's talk about what's on these wires. Okay. So hot 1 is, let's say by convention, okay? Let's just make up this convention here. Line 1 carries what? It carries your 120 volts. That's the potential that's on there. Neutral carries 0 potential, 0 volts. Hot 2 carries 120. But here's where it gets interesting. Hot 2, you can either say hot 1 or hot 2. One of them is called negative 120. Now, there's a reason for this, and we'll get into that when we go into the more details about how the AC current is entering the house. We'll have to get into that discussion with, is a lot more theoretical things with that one. But let's just say for now, at a simplified view of this thing, is that you've got 4 wires, coming into that oven, right? And given that, let's take a look at what it does. Okay, then this is the way I've drawn it now, is pretty much the way they teach it in high school. Okay, we're looking at a circuit purely from a circuit connection perspective. There is no difference whether it is alternating current or direct current. Okay, although there is different mechanisms at play, we do not have to worry about them in terms of what we're doing currently. So let's get into this. Let's go back. Now, we could not troubleshoot this circuit unless we know how the current is flowing within the circuit. So let's go into that. I'm going to have this current simplified diagram here. Okay, so line 1 is your hot 1. So that is, if in case we forgot, let's write, this is our 120 volts. Okay. Neutral, of course, is 0 volts. And line 2 is, we arbitrarily assigned it to negative 120 volts. Now, as I mentioned, we could have assigned line 1 as negative 120 volts and line 2 as positive 120 volts. But it's arbitrary. We can switch to either two. It doesn't matter in terms of this discussion. Now, what we do have to remember, though, when talking about the direction of current flow, we know that the current flows from high potential to lower potential, right? So if I take a look at this circuit diagram now, which way currently does the current flow? Well, we can draw this, we'll change the color, we'll make it green, for example, and we'll just depict the current flow. So since on this diagram, actually, what is the lowest point, right? Lowest potential, and what is highest potential? Of course, the highest potential is 120, and the lowest potential is negative 120, right? And somewhere in between there is 0, right? So in general, we can see that the current flows from high to low. So if we follow these wires, the current flows through here, through the heating element, and over the neutral because it's not connected there, and flows into line 2. That would be the general direction of the flow. Now again, I preface this that this is not exactly true, but it's good enough for the purpose of our explanation here. You will also notice here that from line 1, there's another path of where the current will flow. This will flow from the 120, flow down here. It will go down this circuit, through the light bulb, and light it up, and go to neutral, because 120 volts is higher potential than 0 volts. So therefore the light bulb will light up. So what is actually, we have to go back to what's actually broken in this circuit. Okay, so we're seeing that if the switch is closed, the light bulb is always on. But of course, what's happening is that when the switch is not closed, the light bulb still goes on. So let's go back to draw this diagram here. So at this point in this diagram, we're assuming that the only way that this light bulb can go on is if this switch here somehow bridged itself. And what's happening is the current from L1 is always finding its way down into this flow here, back to neutral. And that's why the light bulb is on and the heating element is not working. All right. So there is another possibility. There is another possibility that this switch is not broken in this way. There's a possibility where, let's erase the switch. Okay. There's a possibility the switch, well, it is broken. The switch, either way, it is broken. But what could be happening is that the switch is closed. It's just that it's always closed and cannot be opened again, right? But all two points are bridged. Now, how can this happen? And the heating element is still not is not getting hot. Well, what can happen here is that because this whole part here is essentially a series circuit, is that if any of these elements has a break in it, like this, if I just erase it, if there's a break in it, or this other switch here, this is, I didn't label, but this was a temperature switch, a temperature fuse or switch. If that is, any one of those can be open, then we will again have this situation where the current is simply just flowing through the light bulb only and not through the heating element, and therefore you can have this situation. But of course, in this case, we knew the switch was broken because no matter which position we turn the knob on the switch, this is a simple rotary switch, what Kenmore calls their infinite switch. So it's just one of these off switches, and then there's various degrees of heat on them. But this was set off position, and in any position here the light would be on, and even in the off position the light will be on. So this is a clear, we at this point just troubleshooting, we don't know, we definitely know the switch is broken, but we also don't know if the heating element is also broken, or perhaps it's the fuse that is broken inside there. Well, it's not really a fuse, it's a secondary switch in there that, you know, turns the heating element off in case of overheat, right? So it could be any one of those two things. But in this video, not really talking about those things. What we really want to talk about is how troubleshooting AC currents, right? And this simplified diagram is fine in terms of tuning. In fact, I had done the actual troubleshooting with a multimeter, and I have confirmed, yes, it is the switch that's broken, and the heating element is also damaged. Okay, there is no connectivity between the two. But because we're going into reading diagrams and looking at AC circuits, I would like to present to you another way in which you could experience these same symptoms, right? And maybe you wouldn't have considered it. And let me show you how that's happening. But before we get into that, I have to go into a deeper explanation of how alternating current really works in order for you to understand this. All right, so let's go. And we have to go back to this diagram, or this convention that we set here. So we said the hot 1 and hot 2 were either 120 volts or negative 120. Okay, so they can't be both, but they can't be both 120 and both negative 120. They have to be at opposite ends. All right, so the simplification we've actually made is that we've taken the time domain out of the equation here. Okay, because as many of us know, alternating current. The reason why it's called alternating current is by definition is because the current is flowing in both directions. Not at the same time, but it's flowing in both directions and changing directions every 1/60th of a second. So in a second, in this, it's basically called, is the frequency of the change is 60 hertz in North America. And that means the direction of the current is changing in 1 second, changing 60 times. All right. So at one moment, you can have 120 volts on hot 1, and you have a minus 120 volts on hot 2, because the current now flows from hot 1 to hot 2, right? But in the very next instant, right, this can be changed. That minus 120 can become 120 volts, and the line 1 becomes minus 120 volts. So then the current in that instance is going this way. So we don't have to get into why this happens, but if we go back to our circuit diagram, we can see that now that the situation is a little bit more complex. Okay, so I have done another diagram here called forward current. Now let's just say the forward current is when line 2 is at its peak, right? The current is on the phase of being positive, so it's now has the higher potential than the line 2. So now let's call this 120 volts here, and let's call this minus 120. So same as on our basic convention, right? So at this point in time, the current is flowing exactly the same way as we have said before, down this way, right? And down this way, right? Laws of electricity always work, right? High potential to low potential, okay? But let me show you that in fact, in the next instant, the current can flow the other way. So I go to this diagram here, the current in reverse. In the next instant, let's use our red here, okay? That line 2 can be 120 volts, neutral will be 0 volts. Line 1 is minus 120 volts. That is just how the electricity is delivered to our house, right? We can go into another explanation on a different video, and I prefer to do that. So if you like these videos, please like and subscribe. I can go into much more detailed on how the electricity is delivered from the power station to our house, into our panels, and into our appliances. But for the sake of this video, so we're just understanding this, we only want to look at this particular circuit and how the alternate current works. So if you like this, please like and subscribe. I will make another video to show how the power delivery system actually works. Okay, so let's get back to this. So because this is higher potential than both 0 and negative 120, current will then flow from this direction. Hop over here through the heating element and down to line 1. Now there's an interesting thing here. Now line 2 is also, what I said, higher potential than 0 volts. So what will come here is that, all right, it'll come down here, take a hop over here, and go here. Now the current will actually will flow down here, okay? But you got to remember that also it's not going to take the 120, although it's higher than the 0 volts, it will take a hop down here and try to get to the 0 volts. Electricity does take all paths. It's a misconception that electricity takes the path of least resistance. It does. That's just a general way of saying it. But I guess a more accurate way of saying it is that it takes the majority of the electricity takes the path of least resistance, right? But it will take a hop over, but very small, and it's so small that it's insignificant for our discussion today. Okay, because we know that on the right side of the heating element is 120 volts, and on the left side is minus 120 volts. And the reason why is because we know that when there's a resistance, it drops all the voltage. And when all the voltage is dropped, it is at its lowest point, which is minus 120 volts. That junction is at minus 120 volts, which means it is much lower potential than on the neutral line, which is 0 volts. Well, then actually, the current will be drawn from neutral down to minus 120 volts. What will actually happen is that this 0 volts, this current, will hop through this light bulb and go down to minus 120. Okay, so on the reverse phase, when everything is on the reverse direction, when everything is working properly, current will flow, as strange as it sounds, because you have 0 volts. 0 volts is higher than 120, and there is current there. It will flow this way through the thing, and it will light the light bulb. So although if we go back to our very simplified diagram here, we've said that this is generally how this thing works, and it is true. It will work this way, right? The light bulb is always on, right? You can see the light bulb. When you turn the switch on, the light bulb is on, right? But when you take a deep dive into it, right, it turns on, the current hits this light bulb in a different way on the second phase, right? On the reverse phase, it actually looks like this, right? Now, it is in a sense symmetrical, and there's nothing wrong with that, right? Because on the green phase, the current was traveling from line 1 into neutral. It's just that in this phase, it is traveling from 0 back to line 1. So it is symmetrical. There's nothing really wrong with this. Okay. So let's look at another scenario, another broken scenario, because we are looking at broken things here, right? It's very possible that we've broken the circuit here. The switch is broken, right? Let's say the switch is broken, completely broken over here, and the light is still on, right? And we also said there was no heat coming from the heating element. This is where things get tricky, and this is where things can fool you if you don't know about the different phases. If we don't look at the time domain part of the alternating current, okay? So, of course, when the switch is broken, let's depict it correctly. So let's look at the scenario that I'm thinking of here, right? So let's look at this. What if this is broken, but as a switch, maybe we don't know how it's made mechanically inside, but what if a piece of metal from the switch has fallen in and bridged these 2 points? And tell me what would happen here? Well, in this case, definitely there would be no current flowing through from the going back to L1 from L2. Definitely not. So this line here from L2 coming through here, that will not flow this way, right? But what might happen, and this line from neutral, going back from neutral to going back to the minus 120, definitely cannot flow because there's no circuit there now, right? So that's broken. So let's erase this line. The question is here, right? If the circuit is wired now this way, which way will the current flow? Which way can it flow? Well, let's color this way. Let's make a blue, or this hypothetical flow here, okay? Because 120 volts is still higher potential than 0 volts, right? It will travel this way, through here, hop over this, through the heating element, through the switch, and down this way through the light bulb and make it to neutral, to 0 volts. Now, will this situation happen? It could. And the reason why it could is because this, and you're thinking, well, how come we don't feel any heat from the heating element when the situation is like this? Well, that can happen because, well, this heating element is only 10 ohms, and it depends, the heat depends on the amperage that's flowing through this heating element, which, because on a series circuit, the component that will limit the largest component, okay, actually all the components on the series circuit will limit the total current that's flowing through the circuit. And because this light bulb has such a high resistance, right, this is going to be the limiting factor to the current, right? So basically, because 10 ohms is so small, you don't even have to consider this in this equation, right? When the current flows through here, that 10 ohms is not going to stop anything, but it's definitely going, this 1000 ohms down here will definitely slow the current down. So current, as you know, is measured in amperes. So while it took these burners are 3000 maybe 1500 to 1500 watts to 3000 watts, right? These light bulbs are probably, as an indicator light, I don't think they'll be more than 1 or 2 watts, 1 to 3 watts, right? So these have very, in another sense, this is a very high resistance, right? And this is it's gonna flow very little current through here, okay? Much less than what is required to actually, actually heat up the heating element, right? Let's just give very simple numbers and divide it, because in order for this heating element to work correctly, to actually feel hot and able to cook things, this is the wattage range that it should be in. Let's just give it, but let's just give a very simple numbers, right? In this case, so we know that watts is power, so its power is P equals V times I, current, right? So if we made the power, the wattage, which is the power, make it a very simple number. Let's say it's P is 12, so it's a little less, right? But doesn't matter. 1200 watts equals to voltage. It had to drop the 120 volts here, and what would be the current then, right? Times I. So the current, to solve this equation, we put this down here, which will give us 1200 over 120 volts, which, because this is simple, we chop it off. This is basically 10, right? 10 amp. So it takes 10 amps to light this one, to make it feel hot. Well, certainly you're not going to get 10 amps through a light bulb. Okay, that would be like that would be the brightest light bulb you've ever seen if it took 10 amps. Okay, so it will not heat up. This heating element is just treated like basically a wire, a straight wire in this case. It's such low resistance. So question is, will this light bulb light up on this flow? It's possible that it will light up, right? But the main point is, we only know that this can happen because of our new knowledge on alternating currents. Okay, so it leads me back to my main motivation for making this video. is like a lot of times when we just know the basic simplification, while this when we just know the basic simplification of electricity, we may not, if we encounter these strange scenarios, there are times when we can't solve the problem with the standard, what's being given to us. So if we just look at going back to this the simplified current and understanding it this way, there is no way that we can see that the light bulb will light up, even in the same situation where we break this switch here, right? If we break this switch here, right? Because this is minus 120, we cannot see the fact that this flow here can also light up this light bulb. It's a simplification, right? But with, I guess, asterisk points, right? If we still do understand the fact that if we understand here and we put asterisks here that this is star minus 120 and this is star, 120 volts, maybe, right? Maybe we'll understand. But always, more knowledge is always useful when troubleshooting these very strange situations. Now, I admit these situations may not actually happen, right? Depending on how the switch is constructed and how it could fail. But failures are failures. Sometimes we don't know how things can fail. So more knowledge is always useful. And again, if you like this video, please like, subscribe, and I will describe the next video. I'm hoping to describe how the electricity is distributed into our house and into our panel, and how the panel is wired. We'll also go touch upon how the neutral and ground is working in your household circuits. So have a nice day and see you in the next one.